Okay, yeah. So, hi everyone. Uh, a very happy new year. So, this class, there was due to some issues. Uh, I had to re-record this class. So this is actually recorded later after the class. I will try to include the questions that were asked during the class in the recording again. So I'll go through everything that we went through in the fifth lecture. And once again, Happy New Year to everyone who is watching this recording. So, up till now, we have discussed. Okay, let me start my pointer. Okay, so up till now, we discussed we have completed module 1 and module 2. Today, we'll finish whatever was left in module 3 and start with module 4. So, till last class, we had discussed calculating the frequency domain output, and we have discussed the frequency dependent media. We will discuss the code today, and then we'll start with the two-dimensional FDTD codes. We'll discuss the FDTD in two dimension, the update equations. And we won't discuss PML today because I did not want to club these two important topics together and burden the my like in create too much burden in one lecture. So we'll do PML tomorrow. So these are the textbooks which are following for this particular course, and so mostly we'll follow this particular book. Where is it? This book by Sullivan, Dennis M. Sullivan. So, electromagnetic simulation using the FDTD method. So we in the module 1 we had covered the basics of EM theory, the the static fields, the time varying fields, time harmonic things, Maxwell's equations, and these two are the textbooks which we referred in this particular lecture. Mm, so the slides were prepared from Sadiku, and I would recommend you to go through David K. Cheng to revise the basics. Really good book. For module in the module 2, we started with the one-dimensional simulation. We discussed the boundary condition, the update equations, the boundary conditions, the stability. We also discussed propagation in dielectric media. And we how to determine the cell size, giving different kind of sources, propagation, lossy media. That we followed these both the textbooks and the codes which we discussed in the class were from the book by Sullivan. Then in the module 3, which we covered in the last class, we discussed we discussed the formulation using flux density, looked at the calculating the frequency domain output, and we saw like how to model frequency dependent media in FDTD. So we'll go over a brief recap of what we did in the last class. So in the last class, had discussed calculating the frequency domain output, and for that we used FFT. Now, since we are dealing with everything in the time domain, we need and some important information can be like we can get better. Some things can be viewed better in the frequency domain results because. So if some signal is periodic, but and it has certain components, but it is not limited in time. It is easier to visualize them in frequency domain. Now, to move from time domain to frequency domain or vice versa, we need to do Fourier analysis. And right now we are like our data is in time domain, and the data which we have is discrete, and we want to get the frequency domain results. So what we need to do is perform discrete Fourier transform on the data available, time domain data with us. Now, to perform DFT, we can employ FFT, which is FFT is the fast Fourier transform. It is an algorithm that is used to compute the discrete Fourier transform, and its inverse can also be done using IFFT. So we will use FFT, and the FFT function is already available with MATLAB, and we won't get into much hassle. We'll use the tool provided by MATLAB to perform to get the frequency domain results generated by our time domain FDTD code. Now, FFT is a very powerful technique. It is used widely, and because it very rapidly computes the DFT. Professor Gilbert Strang had from MIT had said that it is the most important numerical algorithm of our lifetime. Yeah, so we already went over the MATLAB code of performing the F15 in the previous class, but for the sake of completeness, we'll go over it again. So all this thing, this is the simple MATLAB code which we had already discussed in the previous classes. So the instructions for the MATLAB to close all the windows, clear the variables, and clear the command screen. Then we defining the FDTD space. This demarcating the source location or the center of the space as KC, keeping KC1 and KC2 are the two other points where we will probably keep the sources. Here we define the permittivity of the permittivity of free space. We defining the cell size, calculating the time, the, the time step using the Courant limit, and defining this for the space axis for plotting our electric field value. Now we are defining we define the variables for the absorbing boundary conditions, and we are initializing them over here. So this is the ABC initialization. This is the ABC initialization. Similarly, we initialize the ability region with for the electric field and magnetic field EX and HY. Now over here we define the initialize things for the source. The source. Now this is the number of time steps for which the code is to be run, and then we declare a figure window so that we can plot the our electric field results. Uh, so so we create this object for our plot window and then keep the background color as white. Now starting with the main part of the code, so n keeps the track of time. We start with the first time instant and go through n steps, which is the number of time steps that we defined earlier. T1 is used for defining the source. You can also avoid this and directly use n over here. No big deal. So at first we over here we have our we update, and this is the update expression for the electric field. So we update the electric field in terms of the previous electric field and the surrounding magnetic field values. Then if we over here we are using a windowed Gaussian source, which is something like this. So there's this Gaussian window is over there. So we will need a frequency in value which is given over here, and then pulse values delay and that spread, and this t over here is defined over here, which is equal, which has the same values. And so but yeah, so this we defined a source over here. Define the source over here, and after defining the source we just add it to the electric field. So soft source over here, This is the absorbing boundary conditions. We have already discussed this in detail. The, taking the value and putting this in, at the boundary after two steps. Similarly, for the other end, we take this value and put this over here after two steps. Then again, we update the magnetic field over here, HY update. And then we start plotting the electric field. This is the variable that we created for plotting. Like modifying the plot window just to make it look better. All this thing for plotting the window, making it more beautiful and stuff. Then we move to the important part for calculating the FFT, where we store the value. For example, every time we uh, could, and when we generated the source, the pulse value was updated. Now what we do is we store the value which is kept in pulse in a new vector. So EXSRC and ETR so store the values of the pulse and the wave value which is propagating through KE minus 5. For example, if this is our 1D space and this is the window which you see. So something is generated at source over here. So we are generating source over here, and this particular Gaussian pulse or whatever wave travels over here, and when it passes through over here. So and this particular node is KE. So at KE minus 5, for example, over here, whatever the pulse travels, we store the value over here. And once we store it, we get a vector. We have this value. We have all the values that propagated from this point. Similarly, for the pulse value, we get two vectors and we perform FFT on this vector. So we define the FFT length and make sure this is in the order of 2 power n. Then we use this, but and since these two values are real values and FFT, MATLAB performs FFT on complex values. So what we do is we keep the real value over here and keep the imaginary part as 0 and use the complex function to make this real value to complex value and then store it in a separate array. Now, once we do that for both the values, so we have got a complex variable. We have got an array which has complex values. Now, since this FFT should be performed on a vector which has a length of 2 power n, we pad zeros to the. For example, this is the time domain data that we have. Now, this is not in. This has some values less than 2 power n. So for the rest of the values, we will put zeros. So we pad zeros over here and make it the total length of this variable. For example, this was n elements long. We after n elements, this n steps we pad till FFT length the zero values, the complex zeros. Now, once we have got this vectors which is complex and contains the time domain data generated from our code, we perform the FFT function. So we calculate the FFT, normalize it with FFT len, and then I prefer to normalize the total graph with the maximum. We I set the peak value as 1 and all the rest of the peaks near the data relative to this peak. So the maximum peak is always at 1 or 0 dB. Yeah. So once we have so this is not necessary. And over here, we declare a variable df, which is given by this, and this is used so that everything that you have received over here is your y-axis data, y-axis. But what happens to the x-axis? You need something on the x-axis. So this particular part is just we declare a df, we calculate a df, and then we create a vector which will be your x-axis for the data for the FFT data that you generated using the MATLAB function FFT. Now this is these two subplots for the time domain data, and this is how you plot the frequency domain data. So your x-axis is the that we calculated in the last for loop, and on your y-axis is the absolute value of this seed out outsource particular vector where you stored your FFT results of your FFT. So normalizing with M. Yeah, and if you so this absolute gives you magnitude of the frequency domain result, and if you want to see the phase, you have to use uh, I think angle ANGLE. You can check this in MATLAB. Mm, so absolute I think is the magnitude, and angle gives the phase. Yeah, but you can obtain both magnitude and phase results. So this was all that was required for calculating the frequency domain results. We did see the result for Gaussian source, windowed sinusoid, and a sine source. So this is all generated from the code in the previous, like on the previous slide. Now, reformulation using the flux density. This is what we covered in the last class. So for for reformulation in flux density, instead of using Maxwell's equation having electric field, we use the Maxwell's equation having the electric flux density. So we have this three equations, and then we after normalizing them using mm, mm, these expressions, we get the normalized Maxwell's equations, and the flux density is then expressed in terms of permittivity and the electric field, where the permittivity is given by this function, where sigma is the conductivity and epsilon r is the dielectric constant. Now, substituting this inside of over here, so we get and this particular we can see this is a frequency domain result, but our FDTD is a time domain program, the time domain method. So we need this in a time domain. So we substitute the permittivity value in the uh, flux expression for the flux density, and we perform the inverse Fourier transform of the this expression. So we could have also used convolution, but substituting this value and separating like performing IFFT on both the terms is simpler in this case. So you get the inverse Fourier transform of this term over here and inverse Fourier transform of this term over here. And so 1 by j omega is actually integration. And then you break this integration into summation. And then this summation is you take the first term out. And the summation for n minus 1 is then expressed in terms of an auxiliary variable in minus 1. Now this in minus 1 can be expressed this in minus 1 can be expressed in terms of and this in can be expressed in terms of in minus 1 and the present electric field value, and this electric field value can be given in terms of the magnet and the flux density, the in minus 1, and the com- values that are known to us. So once we had the Maxwell's equations, the expression to calculate the electric field from the flux density and In, and the expression for In, we can simply write the computer compatible update equations, where Gx and Gbx are the coefficients which are again calculated in this way. So this is zero point 0.5, this is zero point 0.5, and this is GAX, and this is GBX. Now for the For the case of frequency dependent media, we the frequency dependent media can be given by the Debye formulation, given by Debye. So in this case, this is the expression that is new. After this particular set of permittivity expression was has already been discussed till previous slide. So all we are concerned about now about is this particular term. So for this term, we multiply the electric field with this particular term and write it as SW. Now again, this particular expression is in time domain. To get the is in frequency domain. Now to get this in time Fourier inverse Fourier transform. Now in this case, we know the inverse Fourier transform of this particular part and this particular part. So this term is given by the exponential of mu t, where u is the time is the time unit step function, and E field is then given by AT. So over here, we use the concept of convolution, and then we get the inverse Fourier transform of S omega as ST. We break this integration into the summation, and once and give so this particular ST is now given as Sn. Sn is given by this. We separate this term, and we have the summation. Now Sn can we can write the we can find the Sn minus one as well. So we can find once we got Sn, we can write we find out the expression of Sn minus one, and then write Sn in terms of Sn and electric field value. So now we have a very simple update expression which is very compatible for FDTD, where we calculate Sn by the previous value of Sn and the new electric field value. So the electric flux density can now is given by the permittivity times the electric field. Now permits over here for using the Debye formulation, we saw that the permittivity is given by these three terms, and the first two terms were calculated in using the formulation using flux density, and the third term was discussed in the previous slide. So the first term, it is very simple. The second term is given by recursive auxiliary variable in, and the third term is given by the recursive auxiliary variable Sn. So this can be translated to this expression, where Dn is now given as given in terms of En again, In minus one, En and Sn minus one. So we can rearrange this and to find the electric field in terms of flux density In, the auxiliary variable In, and auxiliary variable Sn, and all the rest coefficient values that is already known to us. So once we had the expression for to calculate the electric field values in terms of In, and we had the expression to calculate In from the previous electric field values and Sn also similarly. So we get the final set of update equations which are computer compatible for MATLAB or Python code for FDTD. Is and these two expressions are we get from the Maxwell's equations. This particular expression gives this update equation for the electric field, which can be calculated from the flux density Ix and Sx, and again Ix is calculated in this form. So update equation for Ix and update equation for Sx. So we have got the set of update equations to calculate the electric flux density, electric field, and magnetic field, and the auxiliary variables. Where and these are the coefficients which are defined over here. So we define the coefficients over here. So this particular this thing is Gx, Gax. This is, I believe, this is, yeah, GBX. This is GCX. And this is del XP. So this is all the formulation behind frequency dependent media. Now, last class we did not look at the code, so yeah, let's take a look at the MATLAB code for the frequency dependent media. This will cover the everything required for the flux for reformulation using flux density as well. So you start with the regular expressions to close the windows, clear the variables, and clear the command window. You define the FDTD simulation space. You define a source location, and the permittivity of free space value, the cell size, calculate the time step from the cell size using the Courant limit. Declare declare a variable z to uh, like keep track of the space axis for plotting for the plot window, and then you define the number of time steps for which your FDTD code is to be run. I so till here I think this is fine. Then we start with the region where we will declare the lossy or the dispersive media. So for our case, this is a 1D case. So, and these are the two boundaries. We define a region where we are viewing, and this region will have and this region's sigma, epsilon r, chi, tau, and other things which will change. So this will remain as air, and this will again remain as air. We'll have absorbing boundary conditions over here, absorbing boundary conditions over here. What changes is that there will be a where uh, region where you will region where we will introduce different permittivity losses uh, and other things. So for that we start with mm, declaring the nodes where the dielectric starts and ends. So this particular place is given by k start, and then this node is given by k end. And then for this region, we define the epsilon r as we define an epsilon r, which for over here is we have kept 4. And then we similarly will define a sigma, a chi, and a tau for the case of dispersive media, lossy media. So if you make this 0, this will become a lossless media. If you make this 0, this will become a non-dispersive media. For dispersive media, you have to keep chi not equal to 0, and for lossy media, you have to keep sigma not equal to 0. Uh, then this particular part is done to define a patch in the plot window. So in the plot window, we want to see the region where we have the slab. So what we do is we we calculate the T min and T max, which for our plot window. So since the plot window is normalized using DDX, over here also we multiply the k start and k end so that we get a T min and T max. So the T min and T max correspond to this particular points in the plot window, uh, and then Y min and Y max are so our plot window is limited by 1 and -1 actually. So anyways, I have taken 3 and -3 as Y min and Y max. So this team in Tmax, 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 Y max, Y max. Okay, so this is not used much. Okay, so we define the vertices. So T min, Y min refers to this particular value. So this is T min, Y min. So this is T min, Y max. This is okay. So this sorry, this is T min, Y max. This is T max, Y max, and this is Tmax Ymin. Okay, so Tmax Ymin. So and F corresponds to the points where these vertices are, so that we can create a face. So this point is as 1. This T min Ymax, T min Ymin as 1, T min Ymax as 2, This is 3 and this is 4. T max y min. Yeah. So once we have noted the nodes, we and like paired the vertices, we will use this for the function patch. You can use help in MATLAB to read more about patch. This was one of the questions asked during the class. So refer to help of MATLAB to read more on patch command. So this patch function can take input in various ways. One of the ways is declare like defining a matrix for vertices and a vector for faces. And you can also input variables directly. So refer to the help section of MATLAB. This is initialization of the absorbing boundary conditions. So we initialize these temporary variables for the ABCs, temp variable for ABCs. Now we initialize the values for the free space for the FDTD variables. So we initialize them with zeros, the the electric flux density, the electric field, the magnetic field, the auxiliary variables that we created N, N, S, N, so Ix and Sx over here. Then the variables for the coefficients of the update equations. So once we have initialized all the variables, then we initialize them with the then we initialize them for the dielectric space. So, for example, this particular region which had different so this region was air. So this was already initialized as gx was 1, gbx was 0, and gcx. So this if the entire region was just air, so if the entire region was just air, so this would till this was fine. But since over here there's a region where we have a dielectric material, so this region will have different properties. So for that, we declare gx. We define gx from k start to k end. So this boundary is k start. This boundary is k end, and within this we define the epsilon, sigma, epsilon z, chi, all these variables. Similarly, we again we define the uh, gbx and gcx between k start and k end, and we modify the coefficients within this. So so once they are modified this, they will implicitly uh, update Maxwell's equation within this region differently as compared to air. And so see, you can see over here that if epsilon r was supposedly 1 and sigma and chi were 0, this region would become this gx will become 1, which will then become air. And sigma, and if they both of them were 0, and gbx and gcx will become 0, and then ix and sx terms will not affect the update equations. So this particular expression is then again for the defining the source. So time, delay, and spread of for a Gaussian source, and frequency for if you're using a sine source. Then you declare the values for you define vectors for storing the values for calculating the FFT. Then you open a figure window. You do the plotting, and like if you want the color of the background to be white, and then this is the video writer file where you create a file with a file name with extension .mp4, create the format as mpeg4, then decide a frame rate, and just open this object file. Now from here, so this is for writing the video file. From here, the main part of the code starts. So this is the update equations for the electric flux density D. Over here, you define the source. Then after you have defined the source, you add it as a soft source over here using pulse. Then this particular set of equation is uh, for the electric field that we saw in the formulation. So since this time the Maxwell's we use the Maxwell's equation where d by dt was given in terms of 1 by root under epsilon naught mu naught dh by dx. Since this was our expression, so this is calculated over here. Now, E is like we saw in the formulation that E was calculated in terms of the flux density, the auxiliary variable I, and auxiliary variable S, and there were coefficients del XP and GX. So the E field is calculated using these terms, and then we update the I auxiliary variable I and S using this expression. So to the previous value, we add the electric field values, and then these are updated. So and over here, so this was discussed in the formulation. This is from the this is the modified Maxwell's equations. This is the absorbing boundary conditions that we have already gone through in details. And now over here, then we update the magnetic field value from the electric field values. And this is the plot window that we have already discussed. So this is the plot window that we have already defined earlier in the beginning of the code. And then over here, we are using this patch function to see the region where everything is happening. We'll see the results in coming slides where you will see. So we had defined F and V earlier, which were the faces and the vertices. Then we are keeping the face color as blue and the opacity very low. So if you make this one, the entire thing will become totally dark. So you won't know what is going behind. But if you keep it low, then you will be able to see the wave propagating inside this patch. So the patch is being used to demarcate the lossy or dispersive region. The patch can be also initialized in this way, where you, instead of using the faces and vertices and functions, you just put the value of the vertices, you put the edge lengths, and yeah, and then give the color, and you can define a patch this way as well. The X label and Y label, the title string which is used inside the plot. Now over here, what you do is you use get frame to store the frame in a in this variable frame n, and then you write this frame n into the writer object. And at the end of the loop, you close the writer object so that your file is saved as a .mp4 file. uh, MP4. If you do not use the close object, your file will get corrupted. Make sure that you remember to close the file. Now, this we already saw while performing FFT. We need to store the data in the electric for the electric fields. For example, if we want the source value and the electric field value which was propagated and near the boundary. This all we saw in for calculating the FFT, and this is for the plot window. So yeah, so in the previous slide, we just where there were the major changes. So instead of using electric field, we are using electric flux density over here. We are calculating the electric field from the flux density, and then we are calculating the magnetic field from the electric field. So these were the major the changes for the places where the changes happened compared to the codes that we had seen earlier. So let's take a look at the results that we got from uh, the new code that we wrote using the electric flux density. So you can see source is given near the left boundary, and as the sine wave propagates towards this dielectric slab. Now this was the slab which we were talking about. So this particular slab is of blue color with blue color, but it looks pink, right? So this is blue color with zero point 0.2 opacity. So you can see what the wave propagating inside. You can see this particular wave is does not get attenuated. What is happening over here is like the reflections along with the forward wave is creating some the standing waves thing is forming over here. But you can see over here this particular thing, this is getting attenuated. So but over here this the wave does not get attenuated. So this is the case of when you keep sigma equal to 0. So this is a lossless media, and when you have sigma as some value, so this becomes a lossy media. So yeah, this is uh, what we get from the formulation using flux. This result was got using formulation using flux density. Now for formulation using for let's take a look at the results for dispersive media. So in the previous case, those were lossy and lossless media, and we did not consider chi as one of them in the variables. So you can see for a lossless non-dispersive media, there will be this pulse, and this pulse as it propagates, and so you see a reflection over here, and then all the cases. So this particular pulse, it does not attenuate inside this, but this particular pulse attenuates, and this particular pulse also attenuates, but you can see this particular spread. So this is asymmetric. So this pulse loses symmetry. And why? For you must remember, for dispersive media, the if a pulse propagates, it will become asymmetric. So it will not be symmetric once if it propagates to a dispersive media. And this happens because different frequency uh, the different wavelengths travel at different velocities. So hence some waves, some frequencies travel at a higher speed and some at lower speed, and what you receive is an asymmetric pulse for dispersive media. Dispersive media, but in case of a non-dispersive, even if the pulse attenuates, it will still be symmetric. This will be asymmetric. Pardon me for my bad writing. So this will be asymmetric. So I'll share these codes, and then you guys can try playing with these variables and the values of sigma and chi and see what happens. So today I'll give your assignment too. So you'll get your assignment too at the end of class, and this which includes this particular thing as well. So you have to vary the values of sigma, chi, epsilon, and see what happens. So we'll start with module 2 now, where so today we'll just discuss FDTD in 2 dimensions. Uh, this will be this PML will be discussed in next class, and we'll try to see if we can cover that in the uh, cover the total and scattered field formulation in the next class, or we can take one more class as well. So the codes for today's class have been taken from this book. Both these books have the FDTD formulation for 2D and 3D. But for keeping the continuity, I'm using this book by Sullivan. You can also refer to the book by Davidson. So when we get to 3D simulation, we'll have to deal with 6 components. The 3 components EX, EY, EZ for the electric field, and similarly for the magnetic field as well. But in case of 2D, we can choose from a group of vectors, from the two group of vectors, having 3 vectors each. So one is the transverse magnetic mode, and one is the transverse electric mode. For a wave propagating in the X, Y, and Z. So, for a wave propagating in the Z direction, uh, transverse magnetic mode does not. So the it does not have hz component. So it has hx and hy, and there is an ez component. Similarly, for a transistor electric mode, it doesn't. So we do not have any ez component. We have an hz component. So we can choose in either choose from either of them. And for our class, we are using the TM mode because the book by Sullivan has the code for the formulations for the TM mode. For the TE mode, you can refer to the book by Davidson. Okay. So once again, we'll start with the normalized Maxwell's equations, and for the since we're going to deal with TM mode, so this will be our set of equations where we have dz and ez, and then we have the two magnetic field expressions hx and hy. Uh, TE case will, since we are discussing TM mode in the class, TE mode will be part of your assignment too. Okay, so I hope everybody can recollect the central difference scheme that we discussed in the beginning of the in the second class. I think in the beginning of the 1D formulation. So for the TM mode, the first Maxwell's equation is given by this particular set of equation. Now over here we have dz, and the dz is a derivative in time. And since this is derivative in time, we and using the central difference scheme, we can write this using this expression. So we have delta t over here, and the future instant the dz at future time instant and dz at past time instant, and at the ij node. So this node is over here, and zooming it, we, you can see this cell over here. So we're trying to calculate the dz over here. Ez or dz, the same thing. So we are trying to calculate dz at this particular point, and so as a derivative at time, so we choose the values at two time instants, n plus half and n minus half, n plus half and comma n minus half. So we get the finite difference approximation for the differential for the time derivative of dz in this form. Now on the right hand side, we have hy and hx. So for both of them, since both of them are derivative in space, and if we assume the delta x equal to delta y, that is, we have square unit cells. So we can give both of them by delta x. So by delta x at the denominator, and we take the and to get it and we want them to be at the same particular point. So we're concerned about this particular point. So we take the hy at the neighboring points, point over here and point over here, and we take these spatial we try to approximate the spatial derivatives using central difference scheme, using hy over here at I minus 1 and I plus 1 comma j terms. So we get the spatial central difference approximation for this hy, and by this expression, and similarly we do this for hx as well. So by taking the value of the magnetic field at the nodes I j plus half and I j minus half for the magnetic field, and so we approximate the magnetic field values as well. So we get we have written the central difference. We got the approximation using the central difference scheme for the first Maxwell's update equation. Now all we have to do is rearrange them. So this is our term of interest. So we can send this on the right hand side, multiply this over here, and then we can get the final update equation, which has this particular which has the electric flux density on the left hand side, which has to be calculated from the past values. For example, this is since this is, you can see this is n plus half, so n minus half and n are the past values, and these are the magnetic field values in the neighboring points. So we have calculated the electric field from the we are using the magnetic field values from the neighboring points to calculate the electric field, and also the electric field value at the same point from a previous time instant. Now, similarly, we go about this for the magnetic field Maxwell's equation as well. So we start. So the second Maxwell's equation for the TM mode is given by this expression. So in the previous class, so in the previous slide, we calculate we use this we use these 4 points and the value at this particular point itself to calculate the electric field value over here. Now we have already updated this particular value in the previous slide. Now we are trying to find out the value over here. So if we if we zoom this over here, so we have updated electric field value over here. And now we want to update the magnetic field value over here. So you can see this is a time derivative. So we split this as in the terms of time. So this is a past value, this is a future value, and taking at this particular node I plus g half. So and there's a we have delta t in the denominator. So this is the central difference approximation, the final difference central difference approximation for the magnetic field in the time for the time derivative. And similarly, we do this for the spatial the derivative of electric field in terms of the spatial derivative there in terms of dy. Since dx, so delta x and delta y are equal, we are using delta x over here. So and we use the neighboring electric field values. So we want to update the magnetic field over here. So we can use a central difference scheme and find out the final difference approximation of the electric field at n using for the n plus half time instant from the neighboring values ei plus ij plus 1 and eij. So using these two nodes, we can approximate the the, the derivative using finite differences, and hence we get the finite difference approximation of this Maxwell's equation. And now since this is the latest value that we want to calculate, we can send this value over here and multiply it with delta t, and we can get the final final update equation for the magnetic field hx. Now, similarly, so over here we used this particular values to calculate this node, to update this node. Now, similarly, we for the TM mode and for the HY magnetic field in the y direction, for we can use the same method. So this is the third Maxwell's equation, and Hy is a time derivative, and so we have updated the electric field over here. We have updated the this particular magnetic field over here, and now we are trying to update this magnetic field over here. So we will use the electric field value over here and here, and using these two electric field values, we'll update this particular magnetic field value. So this can be translated to this cell. So over here, so this is the magnetic field value that we need to update, and these are the two electric field values. So we do the finite difference approximation again for the Hy for the n plus 1 at time instant. So n plus 1 is the future time instant, and n is the past time instant, and this is and delta t in the denominator. So and this is how we get the finite difference approximation for the time derivative of magnetic field at I plus half comma jth node. This particular coefficient again remains the same, and then we have the spatial derivative of electric field in the z direction, and so we have a del x over here, so and delta x over here, and then we will use this the neighboring nodes for the electric field at e I j and I plus 1 j. So the neighboring nodes are used to for the final difference approximation of this derivative. So at the past time instant. So this is so we got the finite difference approximation of the electric field as well. Now, since this is of our interest, we keep this in left hand side, rearrange it we send this to right hand side, and multiply the right hand side with delta. So like this transfer this, and then we will get the update equation for the magnetic HY field. So in all these cases, delta x will be equal to delta y, and we are following the Courant limit. So we had this three Maxwell's equations for the TM mode, and we got the so using the central difference scheme, we got the finite difference approximation for the flux, electric flux density, the magnetic field Hx and Hy. Uh, all we need to do is rearrange them and find out the computer compatible equations. We have seen that delta x is equal to delta y in all this formulation. So for simplifying our for simplifying all these update equations, and we are still following the Courant limit over here. So for 1D, this particular condition is supposed to be delta t should be less than equal to delta x by c. For 2D, this should be root, and this is usually root and n, right? So for 2D, it should be root 2, which is still true if it is if we are considering 2 over here. So because root 2 is around 1.41 or something like this. So we are still following the Courant limit. Okay. So till now we from the first Maxwell's equation we got the central difference approximation. Now rearranging it and writing the computer compatible equation. So this particular multiplying this delta t, if we remove this delta t, add this delta t over here, in this delta t over here. So and this so this particular term comes out to be zero point 0.5. Similarly, over here also, this particular term comes out to be zero point 0.5. And now we send this term over here. So we get the dZij over here in terms of the old value of dz at the same node, and hy in terms of the previous in the surrounding nodes at the previous time incident. So hy ij, and if you want to calculate write this very fast, you just add half wherever you see a fractional value. So you make you add minus half over here, so this becomes half. You again, if you write a minus half over here, you will get this as 1. Similarly, this term over here, if you write a minus half over here, you will get this ig, and if you write a minus half over here, you will get j minus 1. So you got the update equation, the computer compatible update equation for the first Maxwell's equation. Similarly, we will do for the other magnetic fields. Okay. Now, also since this update equations in terms of electric flux density, you will need to compute the electric field as well. So we for also all the formulation that we did for the dispersive media will remain the same. So this particular coefficient is then again calculated using the developments the derivation that we did in for the dispersive media. It will have all those variables you having epsilon r sigma uh, tau chi, and involve sx and ix. So all this thing will be true for this as well. So but right now we will be simulating it for a free space. So gaz just becomes 1. So don't worry, we'll look into this as well. Right now, since this is all so we have free space or air, so this becomes 1. Now Yeah. So similarly for the Maxwell's equation for the magnetic field, we already got the finite difference approximation for both. So again, we rearrange this. We keep delta t over here and send this on the right hand side. So we get this. So we get the magnetic field Hx in terms of electric fields. And again for Hy as well. So we get the Hy in terms of previous Hy magnetic field, that is, and the electric fields. And it follows these two are the conditions that we are seeing. So this is the Courant condition, and we are assuming square grids. Yeah. So and this is all that we needed for the update equations for the TM mode. Yeah. Okay. This slide does not have a TM mode written over here. So TM mode. And yes, so take a look at the results that we have developed like using the code. So using the update equations that we got in the previous slide, I've used those update equations and written the code, and this is what we get. So you can see a Gaussian source is generated over here, and we are using a hard source over here, and the wave propagates in all directions. This particular Gaussian pulse that propagates in all the directions. And so we have run the code till for a limited time before the pulse hits the boundary. So we have not used the absorbing boundary conditions over here. So and that is why we have stopped the simulation before it hits the boundary. Now why? So this is part of your assignment too, that we have the the ABC boundary, the absorbing boundary condition that we discussed for the 1D does not work in this case. And why that does not work is your assignment, is a question. You have to think why the same boundary condition that we discussed for 1D does not work over here. And we'll discuss this answer, but I'll give you some time, some days to think. So I'll share this code with you, and you can run the code. Maybe try adding the boundary condition. I won't. I will give you a clean code without any boundary conditions. You can try adding it yourself and see why it does not work. Yeah. So all the update equations that we developed, the Maxwell's equation and this particular constitutive relation. By using these four equations, we wrote this code. Yeah. So let's take a look at the MATLAB code for the previous simulation. So this code is pretty simple, very similar to what we have already seen. Uh, Okay, so there was a question during the class where whether it would be dz at the center. So one of the formulations that we did, okay, over here. So there's a question whether if we have dz at the center. So ez or dz is fine, both is fine, because they are just related. Dz is just related to ez by this particular expression. So if we find out the electric field, we can find out the flux density, and if we find out the flux density, we can find out the electric field. So yeah, both is fine. And what happens, like whether I'll be discussing spatial dependence of the permittivity in this particular class. So so we won't go to very complex spatial dependence. I'll show simple codes of, for example, if we have this, if we have, so this is our simulation space, and what happens if there was a cylinder and the cylinder had a different permittivity and conductivity, and we had a source, and the wave propagates and hits and the waves get scattered. Something like this will be discussed in class. But anything which is more complex, for example, if the permittivity was a function of space and it varied very differently, or it was very complex, so that won't be covered in class. But I'm sure that whatever formulations that we discussed in the class will be sufficient for you to model all those things. So what happens is, in this case, is what you do is each node is you define the permittivity, conductivity, like everything using the variables, right? You define the coefficient beforehand. So these coefficient you must have seen G A Z G B Z. So all these coefficients, they carry the information of the material, like the media in which the update equation is to be run. So if you change the values of them at these points, so you're defining media in them. So for example, if there was free space, so this would thing would translate to all ones, like for GAZ, so which contain the information on the permittivity. But for example, if this particular had a cylinder, then the corresponding to this particular array, the 2D array, this particular we will define, for example, if its permittivity was 2, this particular the corresponding nodes will have 2 or something, some value stored corresponding to this per cylinder. So if you change the coefficient, so this way you will be able to define the cylinder or any other media in this way. But for example, if the entire space was then again so considered 2, for example, GAZ was 2, then the entire space was a dielectric with permittivity 2. And this is how you model spatial dependence of permittivity. But if something is very complex, then you might have to write your permittivity as a function of x and y, and then generate the matrix and then update this into this particular matrix. But yeah, it will be a few more steps, a little complex, but nothing that you won't be able to do it at the end of this course. Yeah, so this was one question that was raised during the class, and we saw this particular result that there was a hard source and this pulse propagated in the outward direction, and uh, we stopped the simulation before it hit the boundary. Why? Because we have not included the boundary conditions, and we have not included the boundary conditions because the simple ABC that we have discussed for 1D does not work. Why it does not work is part of your question. This question is part of your assignment. And one other question that was raised in the class was, why are we using a hard source over here? So why hard source? So this was not the question of your assignment, but now it is. Why are you using hard source? Okay, my handwriting is so bad. Why hard source? So new question added to your assignment is try soft source. Try soft source and observe. Observe, and with your observations we will discuss why I included hard source over here. So this particular class and this particular simulations, all these are meant for you to visualize and get the idea of how to start working with your code. I could have used soft source, but the response would have been a little different, and visualizing would have become a little different. But again, so this is now your assignment. A good question. Why? What happens if you use a soft source? So now we'll start discussing the code, like what how we went through writing the code for a 2D FDTD code, and for the TM case. The TE case is left as an assignment. Okay, so this is the routine line for MATLAB. You closing all the window. I've commented it over here. So closing all the window, clearing the variable space, and clearing the command window. So in for 1D we had KE, where KE was used to determine the your FDTD space. But since now we are in 2D, so we will be using JE and IE. Okay, IE to denote the number of nodes in the 2D simulation space. So we have 100 nodes on the 100 nodes in this direction, 100 nodes in this direction. Then total 100 cross 100 nodes are there in our simulation space. Now IS and JS refer to the source location, which is at the center. IS, JS, which is at the center. Now we have defined the epsilon z, the permittivity of free space, the cell size, the time step calculated by the Courant condition, and the number of time steps for the code is to be run. Now we this over here we initialize the variables dz and the flux density, the electric field, the magnetic field in x direction and y direction, and ga is your variable for your coefficient for the update equation. So this basically contains the information of the media in the space. So keeping it all one because this but everything over here is air. Now this is time delay and spread for a Gaussian source, frequency for a sine source, or if you are using windowed sinusoid. This is the part where we initialize a plot window, modify it, and open a video writer file and start saving it as a video. So this is for the animation. Somebody asked in the previous class. So here the main part of the code starts. So over here, what we n keeps the track of the time step, and we start from 1 to n steps, which is the total number of steps time steps for which the code is to be run. Since this is a 2D code and we are keeping the track of the x and y direction using j and I. So x direction is taken care by I, and y direction is taken care by j. So since for 1D we had to run one loop, but for 2D we have to run two loops. We are not running it until I equal and j equal to 1 because we do not have the information on the left hand side of the source, and we will let the absorbing boundary conditions to care of when we include them. So right now, dz is updated using this expression, which we developed in our formulation. So dz is updated from a previous dz value and the magnetic field values of hy and hx. Then we define a source, include that so as a hard source over here, and so you can try using soft source, but as this is a part of your assignment. Then again we calculate the Ex from dx from we calculate the electric field from the flux density. We multiply it by this Ga, which is the coefficient and contains information of the media. This is one over here because everything is free space. But in case if it had some different media, this would become this G. This would have some different values, and again, uh, you would have some terms of some IZ and SZ terms would be there, some IZ and SZ terms, and then you would be updating other IZ terms in terms of IZ and SZ terms as well. So that would all happen if we had some different kind of media or complex media over here. But right now we're just simulating in space, so this is fine, and this GA is one. So we have updated the electric field over here. We have updated the electric flux density over here. We had the source over here. Okay, so till over here we have seen in the previous slide, and then we come to updating the magnetic field. So again, we are using two for loops for both of them, updating the magnetic field from the electric fields. Same for Hx and Hy. So we update the magnetic fields over here. Now, for the plotting part, we are use yeah. So I must tell you this. So we are using a surf function over here. For 1D, we used plot. For 1D, we used plot. Okay, this is one. And for 2D, you can use any of these. Mesh, surf. This is mesh. Very bad handwriting. Mesh, surf, and one more, image SC. Image SC. So no space over here. Yeah, image SC. So you can use either of these to plot 2D matrices. So yeah, so 2D arrays, which is matrices, you can use these three functions to plot, to visualize the wave. And then these axes, you have to specify which axis this is and whether how do you want it to be, the limit so you want to limit your z axis to 1, -1, and 1, add a color bar, and so these are for formatting it, the window. And this was important. So this is, you must know if you want, and you'll have to add something. This is create a mesh grid and provide it over here for visualization. So use the help of MATLAB. Use the help option from MATLAB to study, to read more on how this stuff works. Now, including the labels and title and the font size, and all this for the writing the video file and closing the video file. So that was all that we had to we needed for the writing the 2D MATLAB code. And yeah, somebody pointed out rightly that we did not include any absorbing boundary conditions over here. So we have, like, I have not intentionally I've intentionally not included the absorbing boundary conditions over here, because the simple 1D case absorbing boundary condition that we discussed did not work. And and we for this, for 2D, we will be using PML. And since we have not discussed PML, I've missed that, like, I have not included it. And why the simple one does not work is a part of our assignment. And what happens if we do not have a boundary condition? Because in the previous simulation that we saw, the wave did not hit the boundary. But what will happen if it hits the boundary? It is very similar to what happened in the 1D case. So we'll see the results on that as well. Yeah, so okay, so let's take a look at your second assignment. So uh, I had not yet provided you with the code for the lossy media. So I'll give you the code for lossy media as well. So you have to run all the MATLAB codes which are shared with you and inspect each line. If you have any doubts, you can mail me separately or ask in the class. Now, for the code with dispersive media, there will be these parameters: sigma, chi, epsilon r, and tau. Uh, and you have to no, you have to make sigma equal to 0 and chi not equal to 0, and see what happens. Make sigma non-zero and chi as 0. See what happens, and make both of them 0 and see what happens. So some of these results you have already seen in today's class, but yeah, it will be better if you try it out yourself and see how these things vary. It will help you grasp the code better and make you more confident on modifying the codes according to your needs. Now, this was for the till the 1D, and these are for the 2D. So I'll provide you with the 2D code as well, which we saw today. Um, Okay, now what you have to do is, what happens if the code runs longer. So we'll see that also now, and I'll provide the code to you as well. And I've also already told you about why, like, this about this question, like, why does the simple ABC does not work? So you have to think about this. I won't tell it right away. I have an answer with me, and you might find out something better, a better explanation of why does that not work. But yeah, it does not work. Um, we'll see what happens at the boundary. Again, why ABC does not work, and for replacing ABC, we'll discuss PML. Another question that was added was using. You have to try using a soft source. Try soft source. You have to try soft source, and the T case. is left as an assignment. So we have already discussed TM case. The TE case won't be very different. The book by David B. Davidson has all the formulations for TE case. You can refer to this particular book. uh, all the update equations are there. In this book, normalization is not done for the electric and magnetic fields. So some expressions will be the coefficients will be different, but you will be able to see that there is the resemblance between the update equations. Just that the coefficients will be different. So you can take help of this book. Also, you can just Google to get the codes. You can use Google. So you can use Google to get results from MathWorks. So MathWorks has a lot of codes already available by different uploaded by different people, and there are codes by Professor Anant Ramakrishnan. Anant Krishnan. Sorry, Anant Krishnan. And Anant Krishnan. He is a professor at IITB, and he has a lot of courses on NPTEL which are also available on YouTube on computational electromagnetics. So yeah, his course and course by Professor Uday Konkoche. Professor Uday, he is professor at IIT uh, Madras. Uh, so yeah, so both of their codes are available on MathWorks, their groups. You can go through them as well. Yeah. So what happens if there's a wave which propagates till the boundary? So, so we are limited in resources to simulate infinite space. Yeah, right. We cannot simulate an infinite FDTD region. There will have to we are limited in resources. But what happens if we simulate it for longer time and wave hits the boundary? So if we are simulating a wave generated from a point source and propagating free space, the wave propagates outwards and it will eventually come to the edge of the allowable space. It will come to the edge. Now, what will happen? So let's take a look. So a Gaussian pulse is generated at the center of the space, and the wave propagates outwards. As it propagates outwards, and in the absence of absorbing boundary conditions, since they and due to no matching, they get reflected back. So if nothing were done, the reflections would be generated, and the reflections will propagate inwards. Now, as they propagate inwards, they will interact with the region of interest. So, for example, we are interested in something happening over here, and some of the wave that propagated outwards reached the boundary, came back, and then interacted with whatever was happening inside. So there will so once the reflected junk interacts with the things, the wave of the region of our interest, we there will be no way to determine which is the real wave from the reflected thing, and we won't have any proper data which we need. So this is why we need absorbing boundary conditions, because we are limited in space in FDTD, and we we want to simulate it for things for a longer time, maybe for longer data, to view the things for observe it for longer time. But within that time period, some of the waves which generated during the initial part of the program might return back and interact with the program. The waves happening in the center. So yeah, so for this we need proper absorbing boundary conditions, and one of the ways is this perfectly matched layer. So PML was given by Beringer, and this is the best till date. There have been improvements on PML, but yeah, this and there have been numerous approaches to this problem. There have been absorbing boundary conditions given by other people as well, but all of them were limited in some of the other way. But PML was the best. And there have been improvements, but the basic idea given by Beringer is still the same in the PML. So we'll discuss uh, the PML in the next class given by Beringer. So here's a result for both the cases where for both the uh, 2D spaces where one had one which did not have PML and one which had PML. So you can see as the wave reach the edges in the FDTD space which has PML, it gets absorbed or rather matched and dissipated, and and very little or no almost no reflections are returned to the center of the space. But in case of where there was no PML, you can see how all the waves got reflected back, and uh, yeah, so there was reflections and there was no reflections in case of PML. So in today's class, we covered the FDTD in two dimensions, the TM case. TE case is left as assignment. We saw the MATLAB code, and we saw there would be reflections from the boundaries, and we saw why we need PML. So discussions on PML will be covered in tomorrow's class, and we'll see how much of the how much we are able to cover if we need one more class for the total and scattered field formulation. Yeah, that was all for today. Uh, and So this lecture was recorded after the class, and I've tried to include all the questions that were asked during the class itself. And so this recording might be shorter than the total actual length of the class. But and if you have any more questions which whoever is seeing this lecture, you can ask them in the next class or email me. And for anybody else who is not able to access the material on the ISSS portal, please do email me or message me and let me know. So I will share the details. I'll check whether you are already added or not and share the details with you. And if not, I will contact the ISSS admin to add you in the in the as a student on the ISSS portal. So yeah, that is all for today. Wish you a happy new year. So and I'll close the recording for now and upload this on ISSS.